Hello, welcome back to MEC 416/816 Engineering Acoustics. We're going to continue in this lecture on our discussion of single degree freedom harmonic oscillators. And in particular, we're going to talk about mechanical impedance in this lecture. So we're going to consider just a standard harmonic oscillator, in this case with some external forcing in the form of a cosine term, or it could just be a generic forcing. And in this case, we have the following equation of motion. We're going to recast this into complex form. To do that, we're going to cast x into x bar for the complex form, and the f cosine omega t, we're going to recast that as f over bar for a complex amplitude e to the j omega t. And then our equation of motion becomes mx over bar double dot plus bx over bar dot plus kx is now equal to, and that should be an over bar x, f over bar e to the j omega t. And that's now our complex equation of motion. From here, we're going to form an ansatz, and we're going to say that our displacement is equal to some complex amplitude a times e to the j omega t, where a is again complex. We're going to substitute that into equation 59, and we'll get the following. We'll end up with that minus m omega squared plus j omega b plus k times a over bar e to the j omega t is equal to f over bar e to the j omega t. From here, we can eliminate the e to the j omega t, and we'll end up with the quantity minus m omega squared plus j b omega, let's put it like that, plus k times a over bar is equal to f over bar. From here, we're going to solve for a over bar, and this will end up giving us the complex displacement for x, or at least the amplitude of that. We can write this in the following form. We can say that x over bar is equal to 1 divided by j omega times the quantity f over bar times divided by b plus j times the quantity m omega minus k divided by omega. And then differentiating this gives us the complex velocity u over bar, where here u over bar is now equal to the quantity, f over bar. Oh, and I left out the e to the j omega t in equation 62 here. Our velocity is going to be f over bar e to the j omega t divided by b plus j m omega minus k divided by omega. So you can see in this case, the velocity, we lost that j omega in the front. We're going to work now to put this into a simpler form, and we're going to define the mechanical or the complex mechanical impedance to do that. With that being said, the complex mechanical impedance z sub m is going to be z over bar sub m will be equal to, let's just say, some real part, which in this case is going to actually just be b plus j times big X sub m. And in this context, big X sub m is not the maximum steady state or the steady state amplitude. In this case, it is the mechanical reactance. Mechanical reactance, which is equal to X sub m is equal to m omega minus k divided by omega. The benefit of this is then we can write that u over bar, that complex velocity, is now equal to the force F over bar e to the j omega t divided by the mechanical impedance, or in general we can say that some complex f of t divided by that mechanical impedance is equal to our velocity. And what this means is then that z over bar m, or the complex mechanical impedance, is equal to the complex force divided by the complex velocity response, where F here is that externally applied force. This is the mechanical impedance. Now what I'd like you to do is take a moment and think about what the impedance could be a measure of. Pause the video, think for a minute or so about what it could mean physically. Don't look at the notes, just think about it and come up with your own thoughts about what it could be, and then we'll talk about it, what it is when you return. Okay, so the mechanical impedance is a measure of how much a structure resists motion when excited by a harmonic force. So impedance is a resistance to motion when some external force is applied. Here we define a mechanical impedance. When we deal with acoustics, we will look at a couple different types of impedance, including just the acoustic impedance, as well as what is known as the specific acoustic impedance, or the characteristic acoustic impedance. And these two are different. We will end up using the concept of mechanical impedance later on when we deal with acoustics, particularly when we look at pipe systems which have a oscillating driver involved that creates waves that propagate down the pipe. In that case, we'll be looking at how does the mechanical impedance couple to the acoustic impedance. So the key thing about mechanical impedance is that if we know it for a particular driving frequency, then we can immediately determine the complex speed. In fact, specifically, we can write that U over bar is equal to F over bar divided by that mechanical impedance. And then we can use the equation U bar is equal to J omega x to find the complex displacement directly. Or in other words, we can write that x over bar is equal to that force F divided by J omega times Z sub m over bar. And what this means is that if we know what the complex mechanical impedance is, then that's equivalent to having solved the differential equation. It's equivalent to understanding and knowing the dynamics of the system.